Okay, in this video I'm going to be talking about the photoelectric effect. The photoelectric effect was an experiment that changed the way that we think about light. So before we talk about the experiment, I just want to spend a quick second talking about what we thought of light before this experiment came along. Before this, we thought that light was, and it's still part of our current theory, but we thought of light as a varying electromagnetic wave. By electromagnetic wave, I mean a electric force that varies in direction up and down and up and down. So at one point in time, the electric force would be really high, going up, and then it'd get smaller and smaller and smaller, and then it'd actually switch directions, and then come back and switch again. And that's what we mean by a varying electromagnetic wave. Now I've just drawn what might be happening for the electric force, and if we chase that, we can see that it looks like what we usually think of when we think of a wave. We could do in the opposite direction the magnetic field, but I don't want to do that here because I just think the diagram would get complicated and confusing. And so when we thought of that, we said that the height here would be related to the intensity or the brightness of the light. And we thought that this wavelength would be related to the color of the light. And then we also discovered that there are other varying electromagnetic waves that we don't always think of as light because they're outside the visible spectrum, and this is where we related microwaves and infrared and X-rays and gamma rays and all those other things. Again, I don't want to get distracted on that because I still want to focus on what we're talking about with light. So what we thought then was that red light would have a fairly long wavelength, and blue light of the same intensity would be very similar in terms of the amplitude of the wave if the intensity was the same, but that the wavelength for the blue light would be shorter than the wavelength for the red light. Also, just to compare again, a red light with a smaller intensity or a less bright red light we thought would still be a wave, but we just thought of the same wavelength, but we just thought the amplitude of that wave would be much smaller. So this is bright and this is dim, and they're both red light because they share the same wavelength. So that was sort of our theory on light. That's how it got brighter, that's how it changed colors. And there's a whole bunch of theory that you can go back and look into about how if you have a varying electric field, it'll make a magnetic field. And if you have a varying magnetic field, then it'll create a varying electric field. And so if we say that it had both a magnetic field and an electric field and they're varying at the same time, then we could view these two fields as sustaining each other. The magnetic field creates the electric field creates the magnetic field, and back and forth and back and forth. And we get this self-sustaining, repeating field that can represent light. Now, let's get into the photoelectric effect. In the photoelectric effect, they took two pieces of metal and they made a circuit out of it. This is a battery. And then they connected that circuit to an ammeter. Remember, an ammeter measures current. And they set it up like this so we can see it as an open or incomplete circuit. So in this current situation, no electricity would flow because it's an open circuit. There's a gap in the circuit. It's not complete. The electrons can't make it all the way around, so they get stuck and they stop. To complete the circuit then, they decided to try and see if they could use light. The idea was if they sent light in, to this plate, that light, being an electric force, would be able to push the electrons in the metal around. And so they'd go up and down according to being pushed around by this electric force. And if they got pushed around enough that they left their atoms and they could fly through free space, they could fly across this circuit and complete the circuit. And when they completed the circuit, we'd be able to see that by measuring the current that's moving around the circuit. So the idea here was, how much energy of light do we need to get an electron away from this metal so that it can complete this circuit? For the sake of our discussion now, I'm going to focus in then on the key element of this experiment, which is the interaction between the light and that plate. So based on our current theory, when I make the light brighter, so let's make it dim, and then brighter and brighter and brighter. So this is dim, and this is getting brighter. At some point in here, this little electron is going to be forced back and forth and back and forth and back and forth, and at some point, the force on the electron is going to be strong enough for it to leave the plate or the metal. So they did this. They took red light and they put it in and they turned its intensity up and up and up and up and up until they had this huge light coming in and smacking against this thing. And what they discovered is, no matter how intense red light could not get electrons out of the metal to complete the circuit. So they decided to try the experiment again, but this time they switched something about the experiment. This time they used a bluer light. Now they may have gone with something that was even shorter wavelength than blue light, like an ultraviolet light, but for the sake of our discussion, we're just going to use a blue light. And what they discovered was that for even very low intensity blue light, the electrons started to pop off of the surface and they completed the circuit. So this was very strange. This large force, red light, could not free electrons. And this low force, blue light, could. So this did not support the current theory, because here, these electrons should have been only forced with very small forces back and forth, and as a result, the force should not have been enough to let the electrons out. They did notice that when they used a high intensity blue light, that they did get more electrons released. So at least that made sense. But it didn't. What they found is the ability to eject electrons did not depend on intensity in the way that they expected unless they used the right color of light. So the color of light was important. So that's very strange. Now, this experiment, I think, stood for a period of time before somebody came along and explained what was really going on here. And there's a secondary experiment that gives us the same result, but I find the secondary experiment a lot more challenging to understand, so I focus on this one when I'm trying to explain it. But if you look up the ultraviolet catastrophe and the work done by Planck, you can see that his interpretation of that experiment sort of agrees with the interpretation here. And if you put the two things together, you can see they had two strong pieces of evidence for this way of thinking. What they decided was that the intensity of light was not related to the absolute size of the force delivered by the light, but instead reflected the number of light particles. So a high intensity light would be made up of lots of individual light particles. So, and a low intensity light would be related to less of those particles. So turning up the intensity of the light didn't make the individual pieces of light any stronger, it just made more of them. Alternatively, they also discovered that the color of light was related to the size of these individual pieces. So if that's a red one, then a blue piece of light, must be much bigger. So here we can have a red light that's intense. What that means is many small pieces of light. Alternatively, a red light that's not intense means less small pieces of light. But what's important here is because it's red, the size of one piece of light is the same. Alternately, with the blue light, having intense blue light would be like having some large pieces of light. And having a dim blue light would be like having a few large pieces of light. So it wasn't the intensity that changed the amount of energy in an individual piece of light. It was the color. Blue light always comes in large pieces. Red light always comes in small pieces. And the intensity simply reflects how many of those pieces you have. How does this experiment verify that? Well, first of all, let's talk about why we couldn't get any electrons when we had a red light. Again, imagining our two plates, and we're going to send a very high intensity set of red light at that, which means instead of thinking of it as one giant red wave, we're thinking about it as tons and tons of little pieces of light. The problem is that no individual piece of light has enough energy to release an electron. So no matter how many of them you send, none of them can get the job done, and they do not work together. Imagine, for example, that you went to a place where you wanted to buy, I don't know, a cookie. And the cookie cost $1. And they say, we will take loonies for your cookie. You could go in there and you could have $1 million in quarters. And if they're not willing to let you use 4 quarters at the same time, you can't get a cookie. So red light is like having change that they won't accept. It's all too small to individually release one of those electrons. And with money, you could just say, okay, well, I'll use 4 quarters, I'll pay $1 for the cookie. But with light and electrons, they're both so small and so far apart from each other, the chance that 2 pieces of light will work together to try to accomplish one task is very, very, very low. So, if an individual piece of light isn't strong enough, it won't be able to do it, and it doesn't matter how many you send. So you can make that red light as intense as you want to make it. Secondly, then, let's look at why the blue light did work, even when it wasn't very intense. Alternatively, while the blue light intensity was low, the individual pieces of blue light were large. What that means is, despite the fact that there aren't very many of them, each individual piece has enough energy to release a photon. So this guy can do it, and this guy can do it. They can get that electron and it can shoot across. So despite the fact that there's not very many of them, it's a low intensity, the circuit can be completed right away. Again, maybe you even have too much money. Maybe when you come in there and the cookie only costs $1, now you have a $5 bill. It doesn't matter. You can still get a cookie. You can pay the extra money, and then what happens in the physical situation here is that extra money goes into the kinetic energy of the electron, and the electron leaves the plate with more speed based on the fact that you had more energy when you were putting it in. But there's a threshold, or there's a cutoff color where you get to having enough energy, and that cutoff color depends on the metal that you're trying to get the electrons out of. Some metals will release electrons with less energy. Some metals require more energy. So the idea here is that that light must come in these packets. We have a special name for these packets. These packets are called photons. And the individual packets, the energy of one packet, or one photon, is related not to the intensity of the light, but to the color of the light, or the wavelength of the light. We can actually develop a formula here that the energy in light is going to be equal to the number of photons times a special constant that was made up by Planck called Planck's constant, and that's equal to 6.63 times 10 to the negative 34 joule seconds, times the frequency of the light. Remember, frequency and wavelength are related to each other, right? Frequency, if we look at the speed of the wave, we can say that it's equal to the frequency of the wavelength. So when we say frequency here, it's just another way of saying color. The intensity of the light would reflect all three of these factors. For red light, this individual packet size, or the energy for one photon, would just be HF, and that would be small. For blue light, it's a higher frequency, and so it would have a higher energy packet. The photoelectric effect only worked when the individual packets of electrons were bigger. However, when we did make the blue light more intense, that meant we were sending a larger number of strong enough photons, and that meant that we could get many electrons ejected. So what are important takeaways here? Light comes in individual packets called photons. The energy of those photons is related not to the intensity of the light, but to the color or frequency of the light, where red light has small packages of energy and blue light has bigger packages. Ultraviolet, gamma, those are really big packages of energy, and microwave and infrared become smaller and smaller packages of energy. And the overall intensity of the light combines both the size of the package and the number of photons. So if we have an intense red light, that means we have a lot of little packages. And if we have intense blue light, that means we would have less, but the individual packages would be bigger. So that's what we learned from the photoelectric effect. If you're watching this for my chemistry, we're going to go on and talk about how this is related to emission and absorption spectrums in the Bohr atom. And if you're watching this in physics, we'll be focusing on this in terms of how it relates to our overall understanding of light.